All right, we cannot waste even 1 second today because we have too many things to do. Okay. In many ways, the lecture today is going to be a review of some of the things we have seen, but here and there, I'm going to be inserting some extensions, but I will only highlight them. Okay. So everything is going to be about Bayesian linear regression. Okay, so let me start with the picture that we're looking. So we are given some data. Each data point has an input x, the x coordinate, and some response t. And effectively, we're trying to fit a function to the data, but we're doing this in a Bayesian way, which means we want at each x not to have one response, but a distribution of responses. Okay? And what is that distribution of responses going to capture? It's going to capture our uncertainty induced by the fact that we have very limited data, that they're noisy. Okay? So you can see the precise model we're going to use is that at each x we're going to actually assume a distribution that is Gaussian. So this is going to give us the response at that point x, and I call the response here t. Okay? This y of x and w is going to be our mean response, effectively, our regression function, and we will see how it comes in the analysis. All right, so if you have an input that is d-dimensional, okay, this is sort of the simplest possible regression function that you can have. W0 plus all of these things. And you notice here, I am introducing a dummy input x1, or I'm sorry, x0, to account for this bias term w0. So think that this is multiplied by x0 that is always fixed at 1. That's typical, even though today I'm actually going to tell you when you do regression problems to actually get rid of w0 to start with. Okay, so we will see this, how it's going to come up. But if you want to have sort of a generic formulation, you do the summation from 0 to d. So again, in our case, the x's are our input, y is the prediction, and d is the input dimensionality. So I'm going to generalize. Again, we mentioned this a little bit before. So rather than using x1, x2, xd, I'm going to put all the input components to the vector x. You notice x is bold, okay? So that contains my whole input. And instead of using just monomials that we have done before for the input, now I'm going to plug in some functions that I call them regression functions. So you can think these functions being sines, cosines, splines, anything you want to. So effectively, I'm going to write the regression function as W transpose phi of x. So this phi contains all the basis functions, phi0, phi1, phi m minus 1, and x is my input vector. Okay? So again, I'm using the same convention. I put a dummy phi0 there, so I can write this in a unified way as W transpose times phi. The only thing I'm going to say now that when you do regression problems, these functions phi need to be of local support. So don't use a polynomial that is extended all over the space. That is not going to be very helpful. It has to be of local support. All right, so here are some examples. So these are, if we use the monomials that we had before, we will get exactly the formalism we had before. You can use Gaussian basis functions. Square exponentials basically center around mu's with some variance s square. So they look like this, right? They are of local support. You can use sigmoid basis functions that look like this, okay? You can use hyperbolic tangent, and actually, if you read the notes, these are very much related. You can write an expression, a regression model in terms of this to be sort of equivalent for the basis functions are sigmoids, because the two things are related. All right. So this regression function is really my main response. So to actually get a probabilistic model, what we're going to do is we're going to assume that at every x, the response is going to be y of x and w. This is the regression function, plus some noise that I'm making it a Gaussian noise. Okay? This is how we get a probabilistic model. And effectively, this leads to a likelihood that looks like this. And I believe this is what we had stated in the introduction to regression. Okay? So this likelihood model is basically coming from there with a Gaussian noise. So beta is the noise that for now we consider it known, but I will try to address the issue hopefully today on what do we do about beta. But for now, the likelihood is conditional W, is conditional beta, and it looks like this. All right, so what you see here is how this regression function looks when my approximation is like this. W0 plus W1 x1 W2 x2, or here I have quadratic terms as well. Okay, so you can actually play with this very little MATLAB program, and these are the training data, the big dots that you see, and this is the regression surface, the mean response. So at least we can get a visualization. All right, I am going to remind you everything about the MLE estimate for W's and least squares and regularized least squares, and then I'm going to, before we do the Bayesian paradigm, I am going to tell you some pathologies of working with Gaussians, why they're not necessarily always the best. Okay, so let's go rapidly through this MLE estimate for the parameters. So what you see on the top equation, I have collected n data points. So for x1, xn, I give you the targets t1 to tn. So my likelihood, given w, given beta, is the product of these Gaussians. Okay? The only thing that is different from the notation we used before, here is I use basis functions for each training data point xn. Okay? There's really nothing else. Again, this is my likelihood model. So the log likelihood looks like this. And I just indicate all the parameters W and beta that there are known as the vector theta. And often you will see the negative log. So the log likelihood you have to maximize. The negative log likelihood, if you put a minus sign, you have to minimize. And if you expand the negative log likelihood, it looks like this, where you remember one of the terms where the parameters come is this error that you do at your training predictions, at your training data, the error that you do by using this regression function W transpose phi. Okay? And that's why we said that the MLE estimate is the same as minimizing this error, which is basically a least squares problem. Okay? And you can also take derivatives with respect to beta and set them equal to 0, and then beta comes to be the variance defined basically between, from the training inputs. I think you will see the equation written down shortly. All right, so least squares is the same as MLE. Least squares overfits, MLE overfits, so they are not very good. Okay, I'm going to give you these least squares equations in a very compact form. So if you solve for the parameters W, the MLE parameters, by maximizing the likelihood, you basically get this standard nice looking least squares equations. You may have seen this before. Sometimes in my notes, this capital phi, I use it as capital X, all right? So here I just have, I think, following Bishop's notation, capital phi. And if you look carefully, this is very important to remember. Each row in this matrix phi corresponds to one input point. So this is x1, x2. And each row basically evaluates x1 using the basis functions phi0 to phi minus 1. So the way to remember is Each data point you put on every row, x1, x2, and then this involves the basis functions in your regression function. This, in practice, people call it the design metrics, okay? It's completely defined by your data, okay? And so you notice, the dimensionality here is, I have n of those, all right? And I have m basis functions, so it's n times m. And so these matrices are not square, and that's why you have phi transpose phi, which is invertible, and this is called the Moore-Penrose pseudo-inverse, okay? This is your standard least squares problem, okay? If you don't want to do any maximal likelihood, you want to minimize the square error, this is what you get, and this is the phi matrix. So this is the equation I was telling you about, the estimate of the variance. So basically the variance is sort of the empirical variance that you account the square error of the regression function from your target value. So this is exactly the anticipated answer. All right. So I told you I will throw here and there a few new things. So when we did, we expanded the regression function, right, in terms of the basis functions. You remember on the front I had a constant coefficient is bias term. So now I am going to show you actually how you can calculate the bias term completely independent of the rest of the parameters. So that way you only stick with the W's that really are multiplied with these basis functions. So if I am not going to do the derivation, it's here, but look on an exact result that you can show by taking derivatives with respect to W0 and setting them equal to 0. Look at this equation and tell me what is the physical meaning of W0 based on this calculation. So T bar is what? Looking at this, what is this physically? What does it mean? That's the mean of your response at all your data points from your training data. And what is this? This is basically the prediction of your regression function where the basis functions are averaged over the data points. Okay? So the idea here is that if you knew W, then W0 is immediately calculated from this exact formula. So effectively, what we can do is, by doing some centering of the data, we can actually eliminate completely W0, and using centered data, compute these coefficients Wj, and once we're done, we come back to this equation, then we say and W0 equal to that. It's a nice trick that you can do, so the equations look nice, and it's always good to play with centralized, centered data, basically, okay? There are more slides actually that they show you explicitly how to center your data, but effectively you can extrapolate what the idea is from here. Okay, we're supposed to be Bayesian, but you know, since we're doing these squares, right? In case you haven't really seen this, there is a very nice geometric interpretation of least squares and this MLE estimate. So you remember that my design metrics involves these basis functions evaluated for each row at each of the data points. So you can actually see this as one vector, another vector, but what I would like to do is, I would like to see the design metrics by using these column vectors. And each of these column vectors that I denote here with, you notice this phi here is different from that phi. Okay, so I don't, even for Greeks, this is very difficult to distinguish because they're supposed to be the same, okay? So this phi here is a column vector, okay? Of what dimensionality? N-dimensional, okay? So effectively, how many of these column vectors we have? We have really m, right? You can see 0 to m minus 1. So effectively, the space that is spanned by this vectors, this calligraphic phase, is this plane that you see here. So what you have is, you have a response of the system in the n-dimensional space, and actually what you're looking is, you're looking to find an approximation on this subspace S, and the approximation is that subspace, they're really projections to these basis functions. So this projection is phi times W. So you want to project T to that subspace in a way that minimizes the error. So literally, if that subspace is a plate, and your response is here, you project it, and you get phi times W. And the least squares equations, basically what they say is, if you take the vector T minus phi times W, it has to be orthogonal to the subspace, or orthogonal to each of these vectors, and that leads you to basically the least squares equations. Okay, so there is a geometric interpretation basically of the MLE equations that somehow, if you take a course on linear algebra, etc., you will see this written there. Okay, the good news is, if we want to minimize the negative log likelihood, we better be sure that the negative log likelihood is a convex function. All right, so it does happen, and actually in the context of the regression problem, that is the case. Otherwise, we will not be able to find a global minimum. Okay, so the MLE estimate, there is only one of them, and it's uniquely defined. Okay, and it's the global one. Okay, let me throw at you now a concept that we have seen it when we discuss about generalized linear models, and it's an online learning of the parameters W using one data point at a time. So an extremely efficient algorithm that maybe you have never seen, and you're not going to hear this by a statistician because this is a machine learning algorithm. Okay, so remember, MLE estimate is minimizing this. We agree? That's the MLE estimate. And it involves a summation over all the data points. So how do you minimize? You set the derivative of this with respect to W equal to 0, and you solve for W. Now, let's forget the summation and treat one data point at a time. Take the derivative with respect to the W. What do you get? Because this squared, you're going to get Tn minus W transpose phi times phi at xn. So what is the online learning algorithm for W? It is this nice simple equation that you see here that is very general. W at iteration t plus 1 is whatever estimate you get of W before minus what is called some learning rate times the gradient of the error with respect to W, I write here the gradient, so this is the gradient with respect to W, compute it at the data point xn, because I'm going to treat one data point at a time. So look at this equation. Would you like to actually compute W one point at a time using this nice one-line equation? And it converges. So rather than solving the whole least squares problem, you say, okay, take the first point, compute this, start, let's say, from any value, compute this is the new parameter, then plug it in there, take the next point, compute this, keep iterating, and it converges. This algorithm, I demonstrated that it's a generic algorithm for MLE estimates for the exponential family distribution, and it goes with this generic name, least mean squares algorithm, or LMS. Okay, so if you take more courses on learning algorithms for neural network, machine learning, anything basically, this is stochastic gradient descent, and you need to really know it because it's the most efficient way to learn parameters. Nobody wants to invert big equations, least squares, and all these things. Okay. I told you I'm going to be throwing lots of little things in between without proofs. They're in the notes. So let me tell you something that is wrong here. So the error that we minimize, all right, accounts from the square distance of my predictions from my regression function from the training values Tn. So if, let's say, I have somebody gives me one data point that is really an outlier, way out of where it's supposed to be. You notice here it is this error square. So it's penalized a lot. And if you try to minimize this whole error, obviously it will have a significant effect. All right? And you remember I had mentioned very early on in the course that, this, the Gaussians are basically, they're not robust to outliers. And I mentioned some other distributions that they're better to, to robustness basically when you have outliers. Distributions such as the Laplace, and it was on the slide. And here is an example. If these are your training points, but also you have some outliers there, look what happens to the regression function, the least squares. The least squares is pulling basically everything towards the outliers, but if you use an error function not defined by a Gaussian, but by a Laplace or a student t, basically the outliers don't affect anything. And I remind you, the Laplace distribution looks like this. So the likelihood will have basically, instead of square, the absolute error. And when you try to actually minimize the absolute error, all right, the L1 norm, you come up with this huge set of algorithms that go under this generic name that's called lasso. Okay? If you haven't heard the word lasso, if you search again on Wikipedia, you will find millions of references, algorithms ready to go. It's basically another algorithm to do optimization like maximum likelihood estimation, and effectively the probabilistic interpretation is it is based on the Laplace distribution for the likelihood. Now, there are other modifications. Now, the Laplace distribution, you notice, involves absolute value. So if you try to minimize an absolute value, you cannot do like Newton methods, and most of the optimization methods are not going to work properly. So there are various approximations where, for example, in the neighborhood, let's say, of in this location, you use sort of a quadratic, like a Gaussian-like approximation, and far away you use this L1 approximation, and you make them to match together, and so there are various variations, if you like, on how you do this in a robust way, but still use classical optimization methods. But again, if any of you is interested to use the lasso algorithm, you can download it from the author's website from Stanford, and it's ready to go for very large-scale problems, and it has a lot of very nice features that somehow you never get with the Gaussian distribution. So remember lasso, okay? All right. We move then to, we said least squares and MLE is not good, so we introduce the concept of regularization first. So rather than minimizing the square error, you also penalize values of W that they are very high, and this leads to a regularized least squares estimate, that the only thing really you do is you go in the diagonal of this matrix phi transpose phi, and you add this regularization parameter lambda, okay? So can you actually get this, in a Bayesian setting? We will see shortly. That's where the prior is going to come, and it will give us the correct answer. But I want to throw to you now something about the form of this regularization. So here, the regularization is lambda times W transpose W, so that's the magnitude of W squared, okay? You can sort of, so this vector is in m dimensions. I can use any regularizer of this form for any Q. And you see here, I am plotting this term for different Qs. So you can see how it looks for Q equal to 0.5, 1, 2, and 4. For 2, basically, we get the classical thing that we had in the slide before. But what I'm interested to concentrate is on this regularizer for Q equal to 1. And you notice this Q equal to 1 looks, again, it's L1 regularization, so it has some similarities with the lasso algorithm, right? That minimizes the L1 norm. And why I want to tell you about this Q equal to 1? Because when you use L1 regularization, effectively, somehow by the design of this regularizer, many of the W's will turn out to be 0. So the algorithm automatically figures out which W's and which basis functions are needed, and the rest it throws them to 0. And if you want to see this graphically, think of this being our unregularized error function that was basically what we got for the MLE, right, that square quadratic function. And this is a regularizer that says minimize this with this constraint. So this is when you use an L2 regularization. Okay, this is what we saw before, this W transpose W. And this is when you use this L1 regularization that looks like this. Okay, and you notice in this particular case in the schematic, okay, the parameter W1 in the optimizer has been dropped to 0. I know it's a lot of things in your head. The only thing I want you to remember is if you have a very large scale problem and lots of parameters, Lasso introduces sparsity. So the word that you need to remember is if you want a sparse solution, you really need to use L1 minimization. Okay? And Lasso does this for you. So if you have thousands of parameters, it will tell you which ones you don't need to explain the data. And it will do it for you automatically, and this is sort of a pictorial on how this is happening. I will come back to this because I am shortly going to use, on next week I'm going to use this for further discussion on regression problems. All right. So before I go to this fully Bayesian thing and repeat the formulas we had, you may ask me, and what do we do if my response is not a scalar function, but it's a vector? Right? Somehow you have many inputs, the temperature, the humidity, but the response is the life expectancy, the weight of a person, who knows what. What do you do when you have many inputs, many outputs? Can I do this? And the answer is yes, you can. The only difference, so you can make this y to be a vector. The only difference is instead of having w to be a vector and having here a scalar for the regression function, you make w to be a matrix. So you can think of this as many regression problems. You do all of them at once, right? And effectively by making w a matrix, right, you are accounting for the output need to be multivariate. The good or the bad news is if I'm only going to give you the results. Okay, so let's take two extreme cases. Let's take the case that we take a single noise for all the outputs, which we're stretching it, right? You're saying for all the responses, for the height, the weight of people, etc., the life expectancy, I'm going to put the same noise. So if that is the case, it comes out when you do an MLE that effectively the regression models that you're building for each target variable are independent. So effectively what I just showed you with this formulation is like solving, let's say you have, this is a vector in k dimensions, it's like solving k independent least squares problems. So really you're not learning anything new. Now, if it happens and you go in, you put a noise not to be the same, but to be some covariance metric sigma, then the following thing comes, that somehow the coefficients W are independent of sigma. So really, to which extent you are accounting for correlations in your responses, that's questionable, okay? So this will not be an ideal model sort of for doing multi-outputs the way we have it here, okay? The only coupling between the responses is basically that the covariance matrix requires the multivariate response to compute it. Apart from that, the formulas look the same as when, instead of the matrix W, we had simple a vector W. Okay, so let's go through this, the Bayesian version of this. So I'm going back to our standard formulation. This is the likelihood. All right, so the regression function is a vector W transpose times phi. Phi are the basis functions. I am putting a prior on W with some hyperparameters. This is the mean, this is the covariance. And so when you do the algebra, you close the square. You know, you multiply this by this, you close the square. This is the posterior, very nice formula. And the proof is in the notes, so you can read it. It's a good exercise. And the nice thing is, this estimate, basically, of the posterior, you can also do it sequentially, right? Because the Bayesian inference is sequential, so you can actually do this. You can update the parameters mu n and Sn one data point at a time. So if your data are very complicated, very high dimensional, you don't have to save them in the computer, compute all of this, all of that, and then say this is P of W. Well, what you can do is use these equations iteratively, compute, let's say, the covariance and the mean, up to data point n, then get a new point n plus 1 and just update. Use basically the posterior that you had before as your new prior and plug it in on these equations, one data point at a time. The answers look the same. These sequential updates are really preferred because, you know, we work in a regime of high dimensional data, and nobody will allow you to save data forever, especially if you don't need them. All right, we basically, if you want to compute now the maximum of the map estimate, all right, and you take the log of the posterior and you try to maximize this, is the same as minimizing the square error plus the regularization. You see that? From where is this term coming? In the posterior, this comes from the prior, all right? And this comes basically similar to what we had before with the MLE estimate. So when you do a map estimate, it's identical as if you do regularized least squares, but literally for us, we don't want point estimates, we really want to have this whole distribution, right? And I'm gonna show you how the results look when we use this whole distribution. I am not going to have time to discuss about data centering, so I want you to read it, okay? So I want to show you the training of the model for a very simple case, okay? So we're starting with a Gaussian prior, right? So originally, we're going to sample W from the prior because we don't have any data. All right, so when you start, there's no data at all, so your estimate for W comes from the prior, and so these are the contours of the prior, and because it's a Gaussian, they look basically, they're circles, okay, if you manipulate the axis here. So what you see here, you know what they are? It says this is the regression function using samples of W from the prior. If I don't have any data, what is my regression function? W transpose times phi of x. From where is W coming if I don't have any data? It comes as a sample from the prior. So what you see here are all possible solutions of your regression function. All right? Let's collect one data point now. Immediately the likelihood looks like this. And when you update the posterior now, the posterior, it changes shape and becomes data. So here is my data point, and you notice now, if you take samples of W from the posterior, all these regression lines seem to be passing around that point. About, okay? Now let's collect a second data point. The posterior starts becoming more narrow. Now most of these lines are forced to pass through these two data points. If you put more, the posterior and W becomes smaller and smaller. And you remember, at the end of the day, when you have a lot of data, this thing will converge to the delta function to a point, And that point would be really your MLE estimate. Okay? So you can see these are samples of your regression function where the W's come from the posterior. The message here is that when you do Bayesian analysis, you don't get a regression function. You get a distribution. The idea here is one function cannot do the job. You need a distribution over functions, and this is what you see here. Now, lots of people who will take statistics, basically, they will actually learn only one line, and I'm guessing that one line will be for the mean W, all right, and says, oh, that's my regression line. That's not good, because it doesn't tell you the whole truth, okay? All right, this is another version, another software, and by the way, from now on, all your homework problems are going to be computer problems, because I look at homework 2 and I got depressed. Okay, literally, I got depressed. Okay, there will be no more homework 2s like. Okay, I hope my TAs are listening to this video. Okay. So homework 3, we will actually give you the program because it does real large-scale problems. But if you follow the theory and then you look at the program, there is way too much to learn. Okay, but these codes, they're already there. You can download them. There's both Python and MATLAB versions that you can play with. Okay, so nobody cares about W, right? We explained this multiple times. What you really care is if you train the model for some data, bold X and bold T, you would like now for an arbitrary little x to compute what the response is. And that's the predictive distribution. Okay? You are interested on the predictive distribution. I can see so much fascination with your phones, and it's hard for me to believe that you are looking at the presentation, right, on the web. All right. That's why I need to become robotic when I teach, because nothing else will work for me. Right? You agree? All right. Okay, so if you compute the predictive distribution, it looks like Gaussian, and it has this mean, and this variance, that's a function of x. The variance is given like that. And actually, in the notes, I give you some proofs that you may wonder. If you collect more data, do you expect this variance to go down or up? Like if I compute the variance sigma squared n plus 1, so when I have n plus 1 data points, will sigma squared n plus 1 be less or more than this? Less. Okay, so there is a proof in the notes that that's the case. And guess what? If you have lots of data, all of these things, you will get a contribution of 0, and basically then the variance will become the noise in your model. There's nothing you can do beyond that. And you can prove this. Okay? So this thing will actually drop to 0. So basically this is the variance in the predictions induced by the uncertainty W, and this comes from the uncertainty in your model. So the proof again is by closing the square. So what I'm going to do is I'm going to give you some results of this. But you remember I was telling you about this Woodbury formula for manipulating matrices, etc. If you really want to do this calculation sequentially, one data point at a time, beautiful equations actually on computing the predictive variance and the mean in a sequential manner, and they do use these metrics updates that I gave you in an earlier lecture, so you may want to look at them. So let's look at the results. So I have a model that I'm going to train with different data sets, and I'm going to look how the predictive distribution looks like. So in this case, the only data point I have is n equal to 1, so that's the data point. So what is this? This is the mean of the predictive distribution. Straight line. And what do you think are those? Plus minus 1 standard deviation of the predictive distribution. So when somebody tells you, look, you trained the model, give me now, let's say at this location, what is the response? You're going to say the average is this, but my confidence is plus minus that value. And from where is that thing coming? Because the predictive distribution has a mean and it has a variance, right? And these are the error bars. Notice away from the data point, the uncertainty is huge because you have no data, okay? Let me just tell you in general, whatever model you're using, if you're away from the data and the uncertainty doesn't grow, means the model is wrong. And when I say the model is wrong, it's not that you program it wrongly, it may imply that it's a deficiency of the model, because there are lots of models that basically have that issue. So in this case, for example, if the error bars are away from this point and wherever were constant, that would be a problem, okay? So now if we put 2 data points, all right, you notice the uncertainties around the data points reduced. Far away, they're actually very big, okay? If you put now 4 data points, again, you notice the uncertainties here huge, all right, huge. But close to the data points, they look better. And n equal 10, it starts looking very nice, okay? You really have to play with this computer program and run the data and look what the predicted distribution looks like. Verify that the formulas actually come from theory, they're not coming out of magic, and try to get some sense out of this. All right, so this is all the results basically together, okay? And I gave you multiple actually codes written by former students and others to actually see this type of things. One point, right, that I want to make, when you plot basically the predictive uncertainty like this, you don't actually capture how the responses at 2 points are correlated, okay? So basically these error bars don't capture correlations. They're point-wise uncertainties. So if somebody wants to actually see how the response at one point correlates with the response at another point, the only way to do this is by taking samples from your posterior and plotting these regression functions the way that you see it there. All right, so if you want to capture correlations, you really need to go away from these predictive error bars and plot samples of the regression functions coming from different realizations of W's extracted sample from the posterior. Okay, and you can see here, more examples of this. When are we supposed to finish? 12, 20? 20, all right, thank you. All right. So I have, I think, enough time to highlight, and I think this is going to be actually in your next homework set as well. What do we do? What do we do if the noise in the likelihood, right, in our model is not known? Okay. The notation on these remaining few slides is slightly different, only that the design matrix I denoted not as phi, but as capital X, okay? So what did we have before? Here we had before, you remember, all the basis functions, this is a vector, I'm making this to, well, I suppose, let me see. Actually, so y, in the way I have it actually, y, it is a scalar, but this y is all my data to express the likelihood for n data points, okay? So, in any event, I denote this here, the matrix of, the design matrix as capital X, right? The same, slightly different notation from before, this is my design matrix. So, this is the likelihood that we had before, which is a Gaussian. Now what I want to do is I want to take the noise, sigma squared, to be unknown. Because, if somebody gives you data, there's no way you can say, oh, take the noise equal to that. How do you know that? So the noise is unknown, okay? And if something is unknown, means it's a random variable. And now the task will be not only put a prior on W, but also a prior on sigma squared, okay? And not only now produce a posterior on W, but produce a posterior on W and sigma squared jointly. And you may say, at the end of the day, do I really care about sigma squared? No. So what we will do after we do the calculations, average over sigma squared. So we're back to where we used to be with only W, but somehow the fact that sigma squared is unknown will have been accounted for. And you will see that the results are very surprising because the calculations don't look very complicated at the end. Actually, the complexity looks as much as we had before, and in some cases, even simpler. So what prior do we use for the join of W and sigma square? You remember the normal inverse gamma prior that we did? So you basically use for W a normal distribution given sigma square, and for sigma square you use an inverse gamma. And when you do that, surprise, surprise, because the normal inverse gamma is conjugate to this Gaussian, the posterior of W and sigma square comes also to be a normal inverse gamma distribution. Actually, there is no algebra. What you see on this slide, this times that, you can compare term to term. Basically, you get a normal inverse gamma distribution. So the posterior looks a normal inverse gamma distribution. These were the things marked by 0 were the parameters of the prior. The things marked by n now they're the parameters of the posterior. And you notice basically once you collect data, you update the parameters, right? This is a conjugate prior, and these are the final results. So if I write the posterior explicitly, is a normal distribution with these parameters, and an inverse gamma for sigma squared with alpha n and beta n parameters. These formulas that you see there, they're everywhere. If you look on regression papers and statistics, people cut and paste them, and 99% of them don't bother from where they come. They just use them without thinking. Really, the algebra is 2 slides. So don't use anything unless you know from where it comes. All right, so here is the joint distribution. And from the joint distribution, guess what? I can marginalize W out, and the marginal distribution of sigma squared is an inverse gamma distribution. Actually, you can get this directly. And the marginal distribution on W is a student t distribution. Because you remember what's a student t distribution? Is an average of Gaussians of different precisions. And really here, this is what we have, right? If we're going to integrate sigma square, we're averaging Gaussians, take a mixture of Gaussians with different variances, and what it comes out is a student t distribution. But if you have a lot of data, the student t distribution looks like a Gaussian, but it's really a student t distribution. So the marginal posterior looks like this, okay? And I actually give you all the proofs in the notes. You know, again, each proof takes less than a page, but they're in the slides. And the last result I want to show you, okay, now we integrated sigma square out. There is no sigma square, there is only W, and we have the posterior of W. Can we do predictions now? So if you give me some new sets of data points X, and actually here I do it for many test input data X, can you tell me what the output will be? And the answer, of course I can. If you compute the predicted distribution, it comes by a miracle to be a student t distribution that involves basically this parameter Vn, Bn, An, they come from the posterior, and this X curly is basically the new inputs where I want to compute the new output. So everything is in a nice closed form. So really, if you want to do this for large-scale regression problems, there is your student t distribution. Okay? 2 minutes to go. Since we discussed about this general Gaussian inverse gamma distribution for W and sigma square, can we take an informative versions of this? And the answer is yes. And you will see on the next homework, one distribution that you can actually use for a prior is this distribution here. It's a specific form of the normal inverse gamma distribution that I had before, where that matrix there is X transpose X inverse. And X, you remember, is my inputs, right? It's my design matrix. So this looks really weird because you have a prior model, but your prior model depends on your data. You say, wait a second, that's illegal. Well, it's illegal, but it works. Okay? This prior is going with the name Zellner's G prior, G from this coefficient here that you can play with. has a very nice way to interpret it that you can read in the slides, okay? So you can imagine, because everywhere, right, from MLE estimates and everything else, you do get X transpose X inverse. The fact that we have a prior now that is a covariance Z times X transpose X inverse means the calculations look very nice at the end of the day, all right? So this, we will redo actually this type of calculation next week. And I wanted to give you two uninformative priors. So this is one uninformative prior that you can use. Sigma to minus D plus 2, D is the dimensionality of W, all right? So, so if you plug in on the generic expressions these particular values that I have here, some zeros, some infinities, you get that. And also what you can get is, you can get, if you take W and sigma squared to be independent, you get this uninformative prior 1 over sigma squared that I introduced a few lectures ago. Okay? If you actually use this as a prior, it comes that the posterior of W takes the form of a student T distribution. Okay? And the student T distribution has this mean that corresponds to the MLE estimate for W, and it has a covariance basically that is defined by this term here, where, you know, I give you the expression for this metric C, and what is S? S squared is basically evaluated, is basically the square error when W is fixed at the MLE estimate. So you get this wonderful formula, and you may ask me, I'm going to do this fast, right, because we're out of time. I'm going to come back. And why do I really care about this estimates? I am going to give you